So let's take a look at 129. We'll look at part F here, where you're using the ratio test on these series to determine the convergence or divergence. Of course, if you show it's convergent, you're showing absolute convergence in the ratio test. So here's the series we're looking at, and I'm going to call A sub n the terms of the sequence that we're adding up in our series. And if you remember the ratio test, I'll just pull this over here to remind you of how that works for a given series, right? That series is going to be convergent, right? This is the column for convergence, and then this is the column for divergence. We're going to be convergent if the limit as n goes to infinity of the absolute value of the ratio, right, of consecutive terms a sub n plus 1 to a sub n, if that limit evaluates to a real number less than 1. If that evaluates to a real number greater than 1, then the series will diverge. So convergence, if this limit is less than 1, in fact, absolute convergence, right? And here, divergence of the series. If that limit perchance becomes 1, remember this test is inconclusive. You would have to try something else. In the homework for this problem, number 129, if we reach that case, we only state that the ratio test is inconclusive, and that's the end of the problem per the directions. Okay, so let's take a look at it. Remember, a sub n plus 1 divided by a sub n, I can think of as a sub n plus 1 times the reciprocal of a sub n, so that's the way I'm going to think about it. A sub n plus 1, just replace n with n plus 1, gives me this expression. And then here's 1 over a sub n, the reciprocal, right, of a sub n. Recall that 2 to the n plus 1 is 2 to the n times 2. And so this 2 to the n here and this 2 to the n, I can divide numerator and denominator by 2 to the n. And we're just left with this 2 over here. So let's clean this up then. I've got the absolute value, but since n is going to infinity, n plus 1 squared and n squared, of course, are going to be positive even regardless. So we can just get rid of the absolute value bars. So up top, I've got n plus 1 squared. On the bottom, I've got 2 times n squared. So as n goes to infinity, of course, n plus 1 squared is going to infinity, 2n squared is going to infinity. I'm in the infinity over infinity form. I'm going to use L'Hopital's rule then, right? Because this is L'Hopital rule form. Remember, only use L'Hopital's rule if it's infinity over infinity or 0 over 0. Can't use L'Hopital's rule in any other indeterminate form. You can manipulate it to try and get into this form and then use L'Hopital's rule. So here, though, we can use L'Hopital's rule. Like when you do that, make sure you indicate that you're using L'Hopital's rule. You can write it out using L'Hopital's rule, or just indicate that with a little L over the equal sign. So I take the derivative of n plus 1 squared. It's chain rule, really, bring the 2 down. N plus 1 times the derivative of the inner, n plus 1 is just 1. So I get 2 times n plus 1. Here, bring the 2 down. 2 times 2 is 4, n to the first. Notice as n goes to infinity, I'm still in the form infinity over infinity. So I use L'Hopital's rule one more time. Derivative of 2n plus 2, really, if you distribute the 2, is 2, and derivative of 4n is 4. And so that's a constant. So the limit as n goes to infinity is just going to be 2/4, or simplified to 1/2. All right, 1/2 is indeed less than 1. So as we looked at that ratio test, that tells us that our series converges by the ratio test. And so here's an example of how to use the ratio test. Very important test, especially when we look at power series as well.